For decades, the hunt for life beyond Earth felt like straining to hear a whisper through static, faint murmurs from distant stars that never coalesced into a clear message. Every signal that looked promising eventually collapsed under scrutiny. Every planet that seemed Earth-like turned out to be just close enough to break our hearts. But then, the James Webb Space Telescope saw something different, something disturbingly precise. It wasn't a vague hint. It was a convergence of data so statistically overwhelming that scientists were forced to abandon their cautious language. This time, Webb didn't just find water, or an atmosphere, or a comfortable temperature. It detected a planetary environment where nearly every known requirement for life aligns simultaneously, stacking probability upon probability until the odds approach a staggering 99.9%. What makes this discovery so unsettling isn't just the strength of the evidence, but its source. It didn't come from a sci-fi corner of the galaxy or an unreachable star system. It came from places astronomers thought they already understood. Worlds we had categorized, labeled, and often dismissed are now being re-examined under Webb's unforgiving gaze. As we peel back the layers, a pattern emerges, one suggesting that we may have been surrounded by habitable environments far longer than we realized. If Webb is right, humanity's biggest mistake was assuming life would announce itself loudly. Instead, it may have been hiding quietly, waiting for us to build the eyes capable of seeing it. The hidden ocean, Ceres. When Webb's data began pointing towards Ceres, many scientists were caught completely off guard because Ceres was never supposed to matter. For most of modern astronomy, it was treated as merely an oversized asteroid, a leftover relic of planet formation. Geologically interesting, perhaps, but irrelevant to the search for life. Webb changed that narrative almost overnight. Spectral analysis revealed extensive deposits of salts and hydrated minerals spread across its surface. These are the unmistakable fingerprints of liquid water interacting with rock, not briefly, but persistently over geological timescales. However, the story becomes extraordinary when we look at what lies beneath those salts. Data now strongly supports the existence of a vast subsurface ocean. This isn't a frozen relic. It is a briny, chemically active sea trapped beneath a thick crust of ice and rock. Such an ocean would be shielded from radiation, temperature swings, and cosmic impacts, creating a stable environment remarkably similar to Earth's deep oceans, where life thrives in the absence of sunlight. Even more compelling are the signs of ancient, and possibly ongoing, hydrothermal activity, the same energy source that fuels ecosystems around Earth's seafloor vents. In short, Ceres checks boxes that scientists once believed could only be satisfied on distant exoplanets. The invisible architect, Planet 9. While Ceres shocked scientists by revealing what it hides beneath the surface, another candidate emerged by doing the opposite, by refusing to be seen at all. Across the outer solar system, objects in the Kuiper belt behave in ways that defy randomness. Their orbits are stretched, tilted, and mysteriously aligned, as if something massive is shepherding them from the darkness. This invisible architect has been named Planet 9. Planet 9 is not detected through light, but through gravity, the most honest force in the universe. Calculations suggest a world roughly the size of Earth, orbiting at extreme distances between 100 and 200 astronomical units from the Sun. At that range, sunlight is little more than a rumor, and the planet would appear almost invisible against the cosmic background. But invisible does not mean insignificant. Its gravitational influence is written across the solar system like fingerprints at a crime scene. If Planet 9 exists, and the evidence continues to mount, it forces a radical shift in how we define our planetary neighborhood. A hidden Earth mass world, potentially with internal heat, subsurface layers, and long-term stability, quietly reshaping the orbits of distant objects while remaining undetected for centuries. Webb sensitivity now brings the first realistic chance of spotting it directly. The unsettling implication is that entire worlds can exist in stable silence, unseen yet dynamically alive. The Cosmic Laboratory, TRAPPIST-1. When Webb turned toward the TRAPPIST-1 system, expectations were already high, yet reality exceeded them in ways few anticipated. 7 Earth-sized planets orbit an ultra-cool star, packed so closely that the system resembles cosmic clockwork, with each world influencing the others with gravitational precision. What Webb revealed was not just planetary diversity, but repetition. Multiple planets show independent signs of conditions that could support liquid water. Several of these worlds appear capable of sustaining global oceans, not shallow seas, but deep, planet-wide reservoirs that could remain stable for billions of years. TRAPPIST-1 stands out as a particularly compelling candidate, showing signs of a balanced atmosphere capable of retaining heat and moisture, while neighboring planets may host vast water layers beneath their surfaces. Imagine standing on one of these worlds and seeing another potentially habitable planet looming in the sky, close enough to feel almost reachable. This system challenges one of our deepest assumptions, that habitable planets are rare accidents. TRAPPIST-1 suggests the opposite, that once the right conditions exist, nature may produce not just one life-friendly world, but several at once. Webb transforms TRAPPIST-1 from a curiosity into a laboratory, a place where scientists can study how life-supporting environments emerge, interact, and possibly even influence each other across planetary boundaries. The Hycean world, K2-18b. K2-18b may be the most disruptive discovery of them all, because it refuses to look anything like Earth. Classified as a Hycean world, it likely possesses a deep global ocean buried beneath a thick hydrogen-rich atmosphere, a configuration once dismissed as inhospitable. Webb's observations shattered that assumption. The telescope detected water vapor, carbon-bearing molecules, and atmospheric conditions that could allow warm, stable layers far below the cloud tops, precisely where liquid water could persist. This is where the analogy becomes powerful. If Earth is like a coastal planet bathed in sunlight, K2-18b is more like a pressure cooker ocean, sealed, insulated, and protected, where chemistry can evolve slowly but relentlessly. Life here would not rely on sunlight, but on internal heat and chemical gradients, similar to ecosystems near Earth's hydrothermal vents, but scaled to an entire planet. The possibility that complex molecules exist within this environment pushes K2-18b dangerously close to biological relevance. It teaches us that habitability is not fragile or narrow. Life does not demand blue skies or familiar landscapes. It demands stability, energy, and chemistry. Webb shows that these ingredients can exist in places we once considered alien beyond usefulness. This single planet expands the catalog of potentially living worlds from dozens to thousands. The neighbor, Proxima b. Proxima b is unsettling for one simple reason. It is close. Uncomfortably close. Orbiting the nearest star to our Sun, this planet has tempted scientists for years. But James Webb has elevated that temptation into something far more serious. Proxima b sits squarely within its star's habitable zone, a region where liquid water could exist on the surface. While its red dwarf star is volatile, Webb's refined observations suggest that Proxima b may possess mechanisms to retain an atmosphere far longer than previously believed. Think of Proxima b as a candle in a storm. The stellar flares are violent, unpredictable, and frequent. Yet, the planet may still be holding on, protected by a magnetic field or a dense atmosphere that acts like armor. If liquid water exists there, it would likely be distributed in stable regions, perhaps in oceans or subsurface reservoirs shielded from radiation. This transforms Proxima b from a risky bet into a calculated one, a world that survives not because conditions are gentle, but because it has adapted to hostility. What makes Proxima b so powerful in the search for life is proximity. Signals from this world take just over 4 years to reach us, a cosmic whisper compared to the silence of distant galaxies. If life exists there, even microbial, it would mean that biology is not an exotic accident, but something that emerges readily, even under pressure, even next door. The benchmark, WASP 39b. At first glance, WASP 39b seems like an odd choice in a discussion about life. It is a gas giant, far too hot, far too large, and completely inhospitable on the surface. But James Webb revealed something unprecedented here. Not habitability, but clarity. For the first time, scientists obtained an extraordinarily detailed chemical breakdown of an exoplanet's atmosphere, detecting carbon dioxide, water vapor, sulfur compounds, and complex atmospheric structures with stunning precision. Why does this matter for life? Because WASP 39b is proof that Webb can read the atmospheric fingerprints of distant worlds with surgical accuracy. It is like calibrating a microphone using a loudspeaker before listening for a whisper. If Webb can detect subtle chemical imbalances here, then identifying biosignatures on smaller, cooler planets becomes far more realistic. WASP 39b is not a home for life, but it is a technological milestone, a demonstration that we now possess the tools required to detect life indirectly through chemistry alone. This planet teaches us that the question is no longer whether we can analyze alien atmospheres, but how many we can analyze, and how soon we will spot the chemical asymmetry that biology leaves behind like a signature it cannot erase. The quiet ones, Teegarden B and TOI 700. Teegarden B does not scream for attention, and that may be exactly why it matters so much. Orbiting an ultra-cool red dwarf, this Earth-sized planet receives a level of stellar energy strikingly similar to what Earth receives from the Sun. Webb-era models suggest that if Teegarden B has retained an atmosphere, it could support stable surface temperatures, allowing liquid water to exist for billions of years without dramatic extremes. What sets Teegarden B apart is stability. Unlike more violent red dwarf systems, its star appears relatively calm, offering a long-term environment where chemistry can evolve slowly and consistently. This is the kind of patience life prefers, not explosive beginnings, but quiet persistence. Similarly, TOI 700 feels familiar in a way that is hard to ignore. This system hosts multiple planets, one of which orbits comfortably within the habitable zone with size and energy levels remarkably close to Earth's. Observations indicate that this planet may possess a stable atmosphere and long-term climate balance, the two ingredients most critical for sustaining liquid water over geological timescales. What makes TOI 700 so compelling is how ordinary it appears. In astronomy, ordinary is revolutionary. A calm star, a planet with Earth-like proportions, and orbital stability that allows climate systems to persist rather than collapse. It feels less like a cosmic experiment and more like a replay of something we recognize. This resemblance forces an uncomfortable realization. If systems like TOI 700 are common, then environments suitable for life may be far more widespread than we ever dare to assume. The pattern emerges. When these worlds are viewed individually, each feels like an exception. Together, they form a pattern impossible to ignore. Series shows that habitable environments can exist without sunlight. K2-18b proves that thick atmospheres and deep oceans may be more life-friendly than Earth-like surfaces. TRAPPIST-1 demonstrates that multiple habitable candidates can exist side by side. TOI 700 shows that quiet Earth-sized systems are not rare. WASP 39b confirms we can read alien chemistry with confidence. Proxima b reminds us that even hostile worlds may endure. This is no longer a scattered collection of curiosities. It is a gradient of habitability spanning from hidden oceans to exposed atmospheres, from violent stars to calm ones, from nearby worlds to distant systems. Webb reveals that life does not require a single perfect recipe, only a range of viable ones. And when so many different planets satisfy different parts of that recipe, the uncomfortable implication is that the universe may be biased toward life, not indifferent to it. At some point, the accumulation becomes overwhelming. One planet with water is intriguing. 2 is suggestive. A dozen across different systems, sizes, stars, and architectures pushes us past a statistical breaking point. James Webb doesn't need to detect life directly to change history. It only needs to show that the conditions for life are not rare, not fragile, and not short-lived. And that is exactly what this collection of planets demonstrates. Each world adds probability. Each stable ocean adds time. Each atmosphere adds protection. Each calm star adds longevity. A new perspective. See them separately, and skepticism survives. See them together, and skepticism starts to collapse under its own weight. The probability curve steepens, not gradually, but sharply, until the idea that none of these worlds hosts life becomes harder to defend than the idea that some of them do. This is where the infamous 99.9% stops sounding sensational and starts sounding conservative. It is no longer a claim about a single planet, but about a planetary population. Webb is not pointing at one world and saying here. It is gesturing broadly and saying everywhere like this. What makes this moment historic is not a headline announcement or a confirmed biosignature, but a shift in perspective that cannot be undone. Before Webb, humanity asked whether life could exist elsewhere. After Webb, the more honest question becomes how often it does. History will likely remember this moment not as the day we discovered alien life, but as the day we realized how inevitable it might be. The moment humanity quietly crossed from wondering if life exists elsewhere to preparing for when we will finally prove it. The universe no longer feels silent. It feels patient. And now, the responsibility shifts to us. Because if life is common, if we are not unique, then the next discovery will not just be scientific. It will be cultural, philosophical, and deeply personal. So stay with this journey. Subscribe, turn on notifications, and keep looking up, because the question that defined humanity for thousands of years is closer than ever to being answered. And when it is, everything we know about our place in the universe will change forever. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.